Today, we're going to look at pericyclic reactions. Pericyclic reactions are, to me, really the third and final type of reaction when categorizing reactions according to mechanism. Most of the reactions we've studied are polar reactions, those where we have an electron-rich nucleophile reacting with an electron-poor electrophile. We've also looked at radical reactions, where we have unpaired electrons. Pericyclic reactions are a little bit different. In order to be considered pericyclic, a reaction must have a concerted mechanism. And remember, that's just a fancy way of saying that the electrons flow all at once. It's a one-step mechanism. Additionally, the electrons have to flow in a circular manner during the reaction mechanism. When you combine these two facts, you end up with a reaction that has a cyclic transition state. The starting reactant may or may not be cyclic, and the product may or may not be cyclic, but there is a ring formed in the transition state, and that's going to incorporate both fully formed bonds and partly formed bonds. Now, the concerted mechanism and the cyclic transition state together guarantee that these reactions are going to be stereospecific. And remember, stereospecific simply means that the stereochemistry of the product is determined by and predictable based on the stereochemistry of the starting material. Now, in order to study pericyclic reactions, we've got to delve a little bit deeper into molecular orbital theory. Specifically, we're going to look at frontier molecular orbitals, and this is going to simplify things a good bit. Rather than looking at all of the molecular orbitals of a molecule, we only need to concern ourselves with two. Those are the HOMO and the LUMO. The HOMO, that stands for highest occupied molecular orbital. In other words, the highest energy orbital that has at least one electron in it. And the LUMO stands for lowest unoccupied molecular orbital. So again, we're looking at the lowest energy unoccupied or empty orbital. Now, pericyclic reactions deal almost exclusively with pi bonds. And when a molecule has pi bonds, these two FMOs are always going to be either a pi molecular orbital or a non-bonding molecular orbital. So we can ignore all of the sigma molecular orbitals. So let's take a look at a really simple example, the simplest pi-bonded molecule, ethene. Remember how the pi molecular orbitals in ethene are formed. We take a p orbital from each of the two carbons, and we bring them together overlapping either in phase to create the pi bonding molecular orbital or out of phase to create the pi anti-bonding molecular orbital. Because there are two electrons in that pi bond, we simply place them in the lower energy orbital, and that's the bonding orbital. And you can see that the highest energy occupied molecular orbital, the HOMO, is in fact the pi bonding orbital. And that means that the LUMO, the lowest unoccupied molecular orbital, is the anti-bonding orbital. It doesn't have any electrons, and it's the lowest energy orbital that doesn't have any electrons. Typically, when dealing with FMOs, we label each molecular orbital with a Greek letter psi, and then we number them based on their relative energy, giving psi1 to the lowest molecular orbital, and then numbering consecutively upwards. So here we would say that psi1 is the HOMO and psi2 is the LUMO. Let's take a look at a more complicated example. Let's take a look at 1,3-butadiene. Now there are two pi bonds in butadiene, and that means that we have 4 carbon atoms contributing p orbitals into 4 new pi molecular orbitals. Here I've got some molecular orbital diagrams that kind of depict the various levels of bonding in butadiene. You see how in psi1, each pair of adjacent carbons has an in-phase overlap of p orbitals, creating a bonding interaction. So we have 3 bonding interactions, and that's the most bonding interactions that this molecule can have with its p orbitals. And that means that psi1 has the lowest energy and is the most stable of these molecular orbitals. Again, looking at adjacent carbons, looking at psi2, on the left we have an in-phase bonding interaction, and on the right 2 carbons, again, we have an in-phase bonding interaction. But if we look at the middle 2 carbons, here we see an out-of-phase interaction, and that's an anti-bonding interaction. So overall, psi2 has 2 bonding interactions and 1 anti-bonding interaction, and because it has more bonding interactions than anti-bonding, we consider it a bonding molecular orbital. Moving up to psi3, we can see that the outer 2 pairs of carbons, their p orbitals, are aligned out of phase, creating anti-bonding interactions. The 2 middle carbons, those p orbitals, are lined up in phase, creating a bonding interaction. And because we have 2 anti-bonding interactions and 1 bonding interaction, that means that this is going to be an anti-bonding orbital. And then lastly, we have psi4, where every pair of adjacent carbons has their p orbitals connecting out of phase, creating 3 anti-bonding interactions and no bonding interactions. So again, this is going to be an anti-bonding molecular orbital. Now, butadiene, of course, has 4 pi electrons. And if we populate our molecular orbitals with those 4 electrons, we would place 2 into psi1 and 2 into psi2. That means that the highest occupied molecular orbital is going to be psi2, and the lowest unoccupied molecular orbital is going to be psi3. And while this is normally going to be the case for butadiene, we have made one big assumption, and that is that our molecule is in the ground state. We've placed all the electrons into the lowest energy orbitals possible. However, if we were to excite this molecule, say with a photon of ultraviolet light, the molecule could undergo an electronic configurational change. We could, for example, promote one of the electrons in psi2 up to psi3. Now, the orbitals and what they look like haven't changed. However, the FMOs have changed because now psi3 is the highest energy orbital that has an electron. Psi3 is now the HOMO, and psi4 is now the LUMO. So when determining FMOs for a given system, you do have to worry about whether the molecule is in the ground state or an excited state. Typically, ground state configurations are encountered in what we call thermal conditions. The term thermal is really just used to kind of contrast it to what are considered photochemical conditions, because the most common way of getting a molecule into the excited state is through excitation through a photon. There's one last thing we've got to consider when looking at these frontier molecular orbitals, and that is the symmetry of the orbital. If you look at the graphical depictions of these molecular orbitals for butadiene, you can see that there is a pattern of symmetry here. Look at psi1. If you cut the molecule down in half, you can see that the left half perfectly reflects the right half. When comparing the two ends of the pi system, you can see that they are aligned in the same direction. They are in the same phase. In this case, the red lobes are both pointing upwards. Looking at psi2, again cutting it down the middle in half, you can see that the molecule is asymmetric. The phases on either side are opposite. And if you look at the two ends, again, you can see that the orbitals on the ends of the pi system are again out of phase with one another. Here, the left has the red lobe up, and the rightmost orbital has that red lobe pointing down. So we describe psi1 as a symmetric orbital, and we describe psi2 as an asymmetric orbital. Looking at psi3, again, we can see that this is a symmetric orbital, right? If you cut it down the middle, the left side perfectly reflects the right side. And again, the two ends are in phase. Here we have again the red lobes both pointing up on the far left and on the far right. Looking at psi4, again we have now an asymmetric orbital. Now you might notice a pattern here. Psi1 is symmetric, and then it simply alternates from there. Going to psi2 is asymmetric, psi3 is symmetric, psi4 is asymmetric. And this will always be the case. You will always know that psi1, the lowest energy orbital overall, is symmetric, and that they simply alternate going up from there. So those are the basics of FMO theory. And as you're going to see, we're going to make great use of frontier molecular orbitals throughout our discussions on pericyclic reactions. So there are several different types of pericyclic reactions, and we're going to look at the 3 most common types. And those are electrocyklizations, cycloadditions, and sigmatropic rearrangements. So let's start off with what I think is the simplest of those, the electrocyclization reactions. An electrocyclization is a pericyclic reaction in which the molecule undergoes sort of an intramolecular reorganization of pi electrons to make a cyclic product. So here's an example. I've got 1,3,5-hexatriene reacting to form 1,3-cyclohexadiene. Now remember, the mechanisms for all of these pericyclic reactions are concerted. There's just one step. So in this case, we take any one pair of pi electrons, push them down towards the next atom with a pi pair, which then exceeds the octet, pushing that to the next atom. So you have this cyclic flow of electrons, and the direction is really not important. You could go clockwise or counterclockwise. In an electrocyclization, you have a conjugated pi system, and the two ends of that pi system combine to form a new sigma bond, closing up a ring. The two ends of that pi system have to combine in phase in order to make that bond, and they do so via a rotation. When the rotation brings these two ends together in phase, we consider that what's called a symmetry-allowed process. When the two ends of the pi system rotate to form that new sigma bond, each end is free to rotate either clockwise or counterclockwise. When the two ends rotate in the same direction, that is both clockwise or both counterclockwise, we call that conrotatory motion. When they rotate in opposite directions, one clockwise, one counterclockwise, we call that disrotatory motion. So let's draw out what this looks like using a simplified version of our molecular orbitals. Here we're really only concerned with the HOMO when looking at electrocyclizations. With respect to symmetry, these molecular orbitals are going to be either symmetric or asymmetric. So let's take a look at what these two ring closures would actually look like. Here I've got a simplified picture of a symmetric molecular orbital. Now I'm only really drawing out the ends of the pi system, and then I'm kind of looping it around into a ring. We really don't care what's in the middle. We don't really care how many other atoms, how many other orbitals are there. All we really need to concern ourselves with is the symmetry of those ends. Now, in order to bring these two orbitals together in phase to make a new sigma bond, we would have to rotate them in opposite directions. The one on the left would have to rotate clockwise to bring the, let's say, blue lobe inwards, and the one on the right would have to rotate counterclockwise to bring that blue lobe in to create an in-phase interaction. And since one of them is rotating clockwise and one of them is rotating counterclockwise, this is a disrotatory ring closure. Starting with an asymmetric molecular orbital, these two ends would have to rotate in the same direction. If I rotate both of them clockwise, that would bring these blue lobes together, combining the orbitals in phase, and that is a conrotatory closure. Now, as you're going to see, knowing whether the sigma bond formation occurs via a conrotatory or a disrotatory closure is going to allow us to predict the stereochemical outcomes of the reaction. So let's take a look at a couple of actual examples. Here I've got a diene, 2,4-hexadiene. While the molecule itself has 6 carbons, only 4 of those atoms are involved in pi bonds. Now remember, in an electrocyclization, the two ends of the pi system come together to form a new sigma bond and close a ring. So in this case, we're going to make a 4-membered ring. Moving the electrons around in the mechanism, we can also see that we're going to wind up forming a new pi bond between those two existing pi bonds. So we're going to make a substituted cyclobutene. Because this is a di-substituted cyclic compound, we have to worry about the stereochemical relationship between those two substituents. Are they on the same side and cis, or are they on opposite sides and trans? In order to figure out the stereochemical relationship of those two substituents, we have to determine whether that new sigma bond forms via a conrotatory or disrotatory closure. And to do that, we have to look at the frontier molecular orbitals in this system. In this molecule, there are 4 atoms involved in the pi system, each one contributing a p orbital to give us 4 pi molecular orbitals. So with 4 pi orbitals, that means we have psi1 through psi4. And we really don't care exactly what they look like. We really just care about their symmetry. And since we know that psi1 is always symmetric and that the symmetry always alternates from there, we can see that we have a symmetric, asymmetric, symmetric, asymmetric alternating pattern working from psi1 up to psi4. So let's assume that this reaction occurs under thermal conditions, which is usually designated with our big delta representation for heat. Thermal conditions means that we're in the ground state. Now, since this is a diene, that means it has 4 total pi electrons. And we're in the ground state, so we simply place a pair in psi1 and a pair in psi2. Now that we know what orbitals we have and how many electrons we've got, and that we're in the ground state, we can figure out what our frontier molecular orbitals are. In this case, the highest occupied molecular orbital is going to be psi2, and the lowest unoccupied molecular orbital is going to be psi3. But remember, in electrocyclizations, we really only care about the HOMO, not the LUMO. And the HOMO here is asymmetric. So let's draw out our little simplified diagram of an asymmetric molecular orbital, connected by, an undetermined amount of other atoms. In this case, technically 4 total atoms. Note that in our starting molecule, the diene, our 2 substituents, the methyl groups, are both pointing kind of away from the direction where our new sigma bond is going to form, where the ring is going to close. We can attach those 2 methyl groups to the ends of our pi system in our molecular orbital diagram, each pointing away from where the new sigma bond is going to form. Now if we look, because this is an asymmetric molecular orbital, in order to close the ring and bring those two orbitals together in phase, we're going to need a conrotatory closure. Both of these orbitals are going to need to rotate in the same direction. So here I'm drawing them out, both rotating clockwise to bring those two blue lobes together. And look at what that's going to do to our two substituents, our two methyl groups. On the left carbon, that's going to bring that methyl group up by rotating it 90 degrees clockwise. On the right carbon, rotating that 90 degrees clockwise is going to bring that methyl group down. And that means that in our product, we're going to have one methyl group poking up and one pointing down. In other words, the stereochemistry in our product is going to be trans. Now, let's take a look at the same system, but here we're going to alter the conditions. We're going to do this under photochemical conditions. Remember, this doesn't change what orbitals we have, but it does change the identities of the frontier molecular orbitals. So exciting an electron from Psi2 to Psi3 would now mean that Psi3 is the HOMO, and Psi3 is going to be symmetric. So let's draw out our little simplified diagram of a symmetric molecular orbital. Now the starting material here is the same as in the previous example. So again, we can draw in those two methyl substituents, both pointing outwards, away from where the new sigma bond is going to form. In this case, to bring those two orbitals together in phase is going to require a disrotatory motion. Here I have the left one rotating clockwise and the right one rotating counterclockwise. And look at what that's going to do to our two substituents. Rotating the left atom clockwise is going to bring that methyl group up, and rotating the right carbon counterclockwise is going to bring that methyl group up. So they're both going to be pointing up, and that means they're in the same direction, giving us a cis stereochemistry. Now, all other electrocyclizations can be dealt with in the same way. It doesn't matter how many atoms are involved in the pi system, it doesn't matter what those atoms are. All you need to know is how many of those atoms there are, how many atoms are in the pi system, and that will tell you what your molecular orbitals are. You need to know whether it's being done under thermal or photochemical conditions, and that's going to tell you whether you're in the ground state or an excited state, and that will then allow you to determine what the frontier molecular orbitals are. And for electrocyclizations, we only care about the highest occupied molecular orbital. You look at the symmetry of that HOMO, you use that to determine whether the ring closure has to occur via conrotatory or disrotatory closure. You can then draw out a simplified molecular orbital diagram, attach any substituents in the directions that they should be pointing, do the rotation, and see which direction those substituents go relative to one another to determine the stereochemistry in the product.